Each elementary particle has an intrinsic angular momentum, which is called a spin of particle. The Stern-Gerlach experiment are usually used to demonstrate that electrons and atoms have the spin. This experiment involves sending a beam of particles through an inhomogeneous magnetic field and observing their deflection. The result of experiment was rather unexpected. The particles passing through the Stern-Gerlach apparatus are deflected either up or down by a specific amount, while they expected the random and continuous distribution. Let's imagine a particle with spin as a sphere with two magnetic poles, red for south and blue for north. Spin of particle interacts with the external magnetic field. If spin may have any value, then a deviation of particles under the action of the external magnetic field will arbitrary. The Stern-Gerlach experiment showed that spin can have only two values along the external magnetic field, in the same direction or in the opposite direction, which correspond to spin up and spin down, or, more precisely, a projection of the spin on the direction of the external magnetic field. The results of experiment showed that particles possess an intrinsic angular momentum that is closely analogous to the angular momentum of a classically spinning object, but that takes only certain quantized values. Spin of a particle is measured in the units of the spin of photon. It should be discrete, but such particle as electron, proton, neutron have the spin equal to half of unity. Spin was originally conceived as the rotation of a particle around some axis that is related with its magnetic properties. So, we can imagine the particle as sphere and spin as its own rotation. However, really, the particle is not the sphere and spin is a solely quantum mechanical phenomenon. It does not have a counterpart in a classical mechanics, so cannot be interpreted classically or in our usual point of view.